In this video, we will discuss some problems which were previously asked in the GATE examination. In this video, we'll discuss memory. Okay. So the first problem is, in the given figure, the Boolean expression for the outputs in terms of inputs A, B, and C when the clock CK is high. So in this problem, we are supposed to find what is the Boolean expression. Okay, what is the Boolean expression for the output in terms of the inputs A, B, and C when the clock is high. Okay, when the clock is high, okay, what will be the output expression? So that is what we are supposed to find in this problem. Okay, so in this problem, the circuit consists of two levels. Okay, the circuit consists of two levels. So this is your first level and this is your second level. Okay, level 1 and level 2. So I will take this point, this intermediate point, which connects both these two levels of the circuit, this as V X. Okay, and this point as V naught for your understanding. Okay, so I repeat. So here in this circuit, it consists of two levels. Okay, first level is this part of the circuit, the second level, this part of the circuit. Okay, so these two levels interconnected with this line. I'll take this intermediate point as Vx. Okay, Vx, and the output point as V naught. Fine. So here, I'll mark it here. Vx and this is V naught. Fine. Now, so in the given already it's mentioned in the question, when the clock is high, you are supposed to find the Boolean expression. So when the clock is given high, what happens? What happens to these two MOSFETs? Okay, when the clock is given high. So you may be knowing it, so I'll write it here. Okay. When so if one is applied to the PMOS, one is applied to the PMOS, when it's applied to the PMOS, what happens? Is in off condition. Okay, it becomes off condition. That means it acts as an open circuit. Fine. Next, similarly, if the same one is applied to the NMOS, what happens? That particular transistor becomes on. It acts as an short circuit. This acts as an short circuit. So now, based on this concept, so now if you apply one here, what happens is the one is applied to this NMOS. Okay, it becomes on, so it becomes a short circuit. It acts as a short circuit. Okay, similarly, the same one is applied to the P channel. It becomes off. That means it becomes an open circuit. Okay, it becomes as an open circuit. It becomes like this. Okay, so there is no connection between this part, this channel, or this MOSFET as well as this part of the circuit. Okay, so this becomes open circuit and this becomes short circuit. So this is what this clock function. Okay. So now we have to see what this part of the circuit does. Okay. I already told you. Okay. So this consists of two levels. This is level 1, this is level 1, and this is level 2. Fine. Okay, now. So whenever it is in NMOS or PMOS or CMOS, okay, here, whether it is in PMOS circuit or NMOS circuit or CMOS circuit, okay. That is whatever. So this circuit here is an NMOS circuit. So whether what okay. In order to write the expression, if the given circuit, whether it is a PMOS circuit or NMOS circuit or it is CMOS circuit, they can be implemented as a complementary SOP expression. Okay, they can be used to implement using complementary SOP expression. Okay, so that means that is here you see. So I'm going to write the expression for this network 1. So what I told is, so at this point Vx, I'm going to write expression for Vx. That means Vx will be like this. Vx is equal to some SOP expression. Okay, some SOP expression is complementary. Okay, using complementary SOP expression. So we have a complementary SOP expression. So now we are going to write the SOP expression. Okay, now we are going to write the SOP expression. Okay. So to know the number of to know the number of product terms, we have to know the number of parallel paths. Okay, from output to ground. From output to ground. Okay. So if you know how many paths are there, parallel paths are there from output to ground, so you will have that many product terms. Okay. So therefore, the number of product terms is equal to number of parallel paths. Okay. Therefore, number of product terms is equal to number of parallel paths. Okay. So you'll see. So how many parallel paths are there? So if you say take this network 1 with respect to, so this is your output here. This is your output here and this is your ground here. Okay. So you have one parallel path 1, and this is a parallel path 2 with respect to ground. This is 1. Okay. And so this is your parallel path 2. Okay. So you have two parallel paths. So you will have two product terms. Okay. So therefore the expression can be written like this. Vx. Okay. So the expression for Vx can be written as Vx is equal to parallel paths through parallel path through A and C from Vx to ground plus parallel path. Okay, so parallel path. Okay, parallel path to, through B and C. Okay, so the transistor B and C from Vx to ground. So it can be written as, so for the first parallel path from A and C. So it's written as product term P1 plus product term P2. Okay, we have SOP, we have two parallel paths, so we'll have two product terms, so it should be an complementary function. So first parallel path P1 is AC, okay, and second parallel path is through BC, so we are going to write this as BC. This is your SOP expression. Don't forget to put the complement. Okay, so this is your first expression. Okay, so first expression for this network. Okay, so this can also be further written as, it can also written as C, take it common, and can be written as A plus B into C. Okay, so this is the expression for VA. Okay, so we have completed for the first network. Now for the second network. So this is the second network. So now to write expression for V naught. So V naught is equal to similarly an SOP function in complemented form. So now if you take here, so with respect to output to ground, we have only one MOSFET. Okay, so it will be very easy. So we have only one part, so only one product. Okay, so I'll put as P1. Okay, so what will be written as? So what is the P1 here? So what is the input for this transistor? It's nothing but this Vx. Okay, nothing but this Vx. So I'll write this as Vx complementary. Okay, so therefore the expression for Vx already written here. What is the expression for Vx? A plus B into C the whole bar. So this is expression for Vx, and this complement we have. Okay, so now we have two complements. Okay, which cancels each other. So therefore your final expression is, okay, therefore your final expression is A plus B into C. Okay, so this is your final expression, Boolean expression for the output in terms of A, B, and C when the clock is high. Okay, so this is your final answer. So we'll move to the next question. So in this question, a ROM is used to implement the Boolean functions given below. The function f of 1 a b c d is equal to a b c d plus a dash b dash c dash d dash. F2 is equal to a plus b into a dash plus b dash plus c, and function f3 is equal to summation of 13 and 14. So in this problem, you are asked to find what is the minimum size of the ROM required. First part, and second part, determine the data in each location. Okay, determine the data in each location of the ROM. So this is Arjun, a 5-mark question. So now we'll discuss this. Okay, these two answers. Okay, so what is memory? You see, first what is memory? So memory is nothing but storing a particular data. Storing a particular data, a particular address location. Okay. So this is in short description of what is memory. Okay. So now we see a general diagram of a ROM. Okay. General diagram of a ROM. I will say we'll take a ROM. Okay. So general diagram of a ROM is represented as. So now 2 power n cross m. So this is your general representation of RAM. So what is n and what is n? So n is nothing but number of inputs. And what is m? M is number of outputs. Okay. So now n is nothing but number of inputs and m is nothing but number of outputs. So it can be represented in the diagram like this. Okay. So 1, 2, 3, so on till m. Okay. So in order this is here 2 power n is nothing but your memory location. So where n is the number of inputs. So the number of inputs is like 1, 2, so on till n. Okay. So these are your number of inputs, and this is number of inputs, and this is number of outputs. And so we have 2 power n memory location. So for example, if n is equal to 4, okay, if n is equal to 4, so what is 2 power n? So 2 power n is equal to 2 power 4, which is nothing but 2 power 4, 16. So we'll have 16 address location. Okay, so we'll have 16 address location. Okay, this is just an example. Okay, n is equal to 4. So now, so from the given problem, we will see how many number of inputs and how many number of outputs. Okay. So these are here. So what is the number of inputs? So number of inputs n. Okay. So what is the inputs here? F1 number of inputs A, B, C, and D. Okay. Number of inputs A, B, C, and D. So the number of inputs is equal to 4. And number of outputs is nothing but F1, F2, and F3 is nothing but is equal to 3. So what should be, so what is the minimum size of the ROM required? So that is nothing but for 2 power 4, n is 4 plus 3. So 2 power 4 plus 3, nothing but 16 cross 3. Okay, 16 cross 3. So this should be the minimum size of the ROM required to implement the given expression. Right. So now we will go to the second part, B. So what is B? So you have to determine the data in each location of the RAM. Okay, to determine the location data in each location of the RAM. So in order to do that, you have to find what are the functions. So f of 1, a function 1 is equal to. So what are the functions here? A, B, C, D plus A dash, B dash, C dash, D dash. So write this corresponding minterms here. The corresponding minterms for this is M. So you should be knowing this, how to write the minterm values. So if a dash is present, you have to put 0. If dash is not present, you have to put 1. 1, 1, 1, 1. Here are all zeros, 0, 0, 0, 0. Okay. So just add the corresponding values. So 8, if it is on 4-bit, use 8421. Use 8421. So just write the corresponding value. So you have 4 ones here. So add all the 4 variables. 8 plus 4, 12, 13, 14, 15. So M15, okay. M15 plus M0. So function F1 is nothing but summation of M in terms, that is 0 and 50. So now go to the F2. Okay, now we'll go to the F2. So now, so this is the given function A plus B into A dash plus B dash plus C. Okay. So now in order to find this, I'll write this. So the given function A plus B into A dash plus B dash plus C. So this is the given function. So now in order to find the minterms, so just multiply these two. Okay. So you have to multiply. So this A multiply with all the literals here. And similarly B multiply with all the literals to get the corresponding product. Okay. So now A into A dash plus A into B dash plus A into C plus now B into A dash. So I'll write it like A dash B. Okay, write in order. A dash B and then B into B dash plus B into C. Okay. So now here you can see A into A dash. A into A dash is nothing but equal to 0. Similarly, B into B dash is also equal to 0. So what is the term left out? So A into B dash plus AC plus A dash B plus B. So now we have to find the corresponding, okay, we have to find the corresponding minterm. Either you can insert the missing letters or you can plot the corresponding ones in the four variable k-map. So whichever is easy, you can follow it. Okay. So now I will be solving this thing by inserting the missing letters. A, B dash, C into C dash. Okay. Missing letter is C plus C dash. Because C plus C dash is equal to 1. Okay. Next, AC into, here B is missing. So B plus B dash. Next, here C is missing. C plus C dash. Here again A is missing. Okay. B, C, like this. Here A is missing. So A plus A dash. So now just multiply it. And see that you write in order. So A, B dash, C plus A, B dash, C dash plus A, B, C plus A, B dash, C plus A dash, B, C plus A dash, B, C dash plus A, B, C plus A dash, B. Okay, so the next step is find if we have any repeated terms. Okay, we find any repeated terms. Here you can see ABC is repeated twice. ABC, and here also we have ABC. Okay, so remove, you can neglect one term. Similarly, A B dash C is also repeated twice. So leave one. Okay, next A B dash C dash. Okay, A dash B C. So remaining all are present. So like this you can solve, or else you can solve this by using an K-map. So I think the K-map method will be very easy for you. So I'll explain that method also. Okay. Okay. So now we will take an four variable K-map. Okay. We'll take an four variable K-map. So what are the variables? A, B, C, D. So I'll put A, B, C, D. So out of these two methods, I feel this is the easiest method of the two. 0, 0, 0, 1, 1, 1. So you have a four variable. So now what you are going to do is you are just going to implement these terms. Okay, you're going to implement these product terms in the K-map. So now if you take A B dash, so A B dash means so it will be of these terms. Okay, A B dash. So A into B dash. So you should have four ones like this, so that you get a product terms like A B dash. Similarly, second one AC. AC na, so these two should be A and C. C should be these two. So okay, A means it should have these two rows. C it should have these two columns. That means these two plus these two. That means here. Got it? So it should have these four ones. Fine. Next, A dash B. A dash B means A dash B. So you have four ones here. Fine. And last BC. So BC means this BC means these two rows with these two columns. Okay, that means this square. Okay, so it's already plotted, so we can leave it. Okay, so these are the number of midterms. So this is easy method of finding the midterm values. So now you can write the midterm values. So this is 0, 1, 2, 3, and this is 4. So write the corresponding midterm values. Summation of M 4. Okay. This is 0, 1, 2, 3. This is 4, 5, 6, 7. 4, 5, 6, 7. Okay. 8, 9, 10, 11. 8, 9, 10, 11, 11, 12, 13 is not there, and 14, 15. 14 and 15. So these are the minterm values for your function f2. And finally, for the function f3, it's already given in the question as okay as 13 and 15. 13 and 15. Okay. So these are the functions for this given problem. So now, put this here. So now we'll see. We'll determine what is the data on each location. So this is an 4 bit. So it will be A, B, C, D. I'll write it here. So A, B, C, and D. So now we'll determine what is the data on each location of the RAM with inputs A, B, C, D, and outputs F1, F2, and F3. Okay, so the possible combinations of inputs for four variables are 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Next, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1. Next one, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. And finally, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. So these are the min terms for the given inputs. Now we are going to plot what is the data for each location of the RAM. So these are the memory locations, or we can say address locations. Okay, so these are nothing but your address locations. So 16. So 16 address location. Okay, and so now for function F1, function F1 0 and 15. So 0 and 50. So remaining are all 0. 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. So this is the data for F1 output. For F2, 0, 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 is not there. And 14, 15. Finally, 13, 15. So 0, 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14. 15. So this is your final answer. So these are the data which will be present. So now, for example, the given input is here is 1001. Okay, so the given input 1001. So this is the data present. Data on the output here. Okay, 010. Okay, for the given input. Okay, and if the given input is 0101, the output is 010. So these are the data in each location of the RAM. Okay, so now move to the next problem. Okay, so in this problem, a dynamic RAM cell which holds 5 volts has to be refreshed every 20 milliseconds so that the stored voltage does not fall by more than 0.5 volts. If the cell has a constant discharge current of 0.1 picoamps, the storage capacitance of the cell is. Okay. So what does this question tell you? It's nothing but a dynamic RAM. You have a dynamic RAM cell which holds a 5 volt. Okay, which holds a voltage of 5 volts. That has to be refreshed every 20 milliseconds. Okay. So that the stored voltage does not fall below, or it does not fall by more than 0.5 volt. Okay. So you know what is the structure of dynamic RAM cell. So dynamic RAM cell consists of normally one NMOS enhancement MOSFET followed by an capacitor. Okay, so what will be the structure will be like this. Here MOSFET. Okay, here MOSFET followed by an capacitor. And this is your bit line. This is your bit line DL. And this is your MOSFET. Here MOSFET, and this is your capacitor. Okay. So when so when the transistor T is on, okay, the transistor T is on, capacitor C is charged to the bit line value. Okay, it's charged to the bit line value. Here the bit line value is nothing but 5 volt. That is VC is equal to 5 volt. Fine. When the T is off. Okay. When the transistor T is in off condition, capacitor will start discharging. Capacitor C discharges. So this is the condition of the MOSFET and the capacitor. Fine. So now we'll see in the same diagram when the transistor is in off condition. So this is a bit line. This is your bit line. This is your MOSFET. So when the MOSFET is said to be in off condition, okay, what happens is nothing but the gate and source. You don't have any connection between these two. Okay, and we have a capacitor here. This connected to the ground here. It starts discharge. So it is storing a 5 volt. Okay, so your voltage starts decreasing by del V. Okay. So now we'll see the relation between the current voltage and the transistor. Okay. I'll try the relation between current I, voltage V, and time T. Okay, can be written as ID is equal to C into dV by dt. Okay. So now constant discharge current ID. Okay. Constant discharge current ID can be written as C into del V by CV. So now del V is nothing but change in voltage. Change in voltage. TD is nothing but time of discharge. Okay. C is number C. So you are supposed to find what is the capacitance value. Okay. So which can be written as C is equal to your ID. That is nothing but discharge current into TD divided by del V, which is equal to. So what is your ID from your given question? 0.5 picoamp into TD is nothing but 20 milliseconds. 20 milliseconds divided by del V, change in voltage. Change in voltage here is more than 0.5 volts. So when you substitute all these values, you'll be getting 2 into divided by 0.5 is equal to 4 into 10 power minus 15 farad. So 4 into 10 power minus 15 farad, D is your correct. Yes. So we'll stop the video with this. We'll continue the other problems in the next video. We'll discuss some problems related to digital electronics. These problems are asked in the topic memory. So in this problem, for the NMOS logic gate shown in the figure, the logic function implemented is. So for the given logic circuit, we are supposed to find what is the logic function it is going to implement. So we already know that for an NMOS circuitry, okay, for an NMOS circuitry or PMOS or an CMOS circuitry, the expression, the logical expression will be expressed as, okay, logical function will be expressed as a complement of the SOP expression. Okay. For any NMOS or PMOS or CMOS circuitry. Okay. So the expression will be given as SOP expression, which is will be in complemented form. Okay. In complemented form. Okay. So it will be like this. So we have to find the SOP expression here. So the SOP expression is under the product terms. Okay. Product terms 1, 2, can be any number. Okay. But in the complemented. Okay. So these product terms are nothing but the parallel paths. Okay, each product terms is nothing but the parallel path from the output terminal. So this is your output terminal. From the output terminal with respect to the ground. Okay, so each product term is nothing but which are arranged in parallel paths between the output node and the ground. So now we'll see how many parallel paths are there between the output terminal and the ground. Okay. So now if you see here, so this is your output terminal, right? And this is a ground. So we have one parallel path, you have two parallel paths, and third you have three parallel paths. So therefore, your function f is equal to, okay, first parallel path. That is your product one, second parallel path, which is nothing but product two, and your third parallel path, which is nothing but your product three. Okay, so this will be complement. Okay, so first we are going to write for the first parallel path. I'm going to write this as P1. Okay, so this is P2 and this is P2. Okay, so parallel paths between the output terminal and the ground. Okay, now, so what is the first parallel path between what are the transistors? A and B. So first parallel P1 is going to be AB. Okay. Second parallel path is going to be A and C. Okay. Plus the third parallel path is going to be D and E. Okay. D and E. Okay. And all this is an SOP. This is your SOP expression, which is complementary. Complementary. Okay. So now this expression can be further written as or further simplified as, I'm going to take this A term common. Okay. So A taking common, A into B plus C plus D E. So this is your final answer. So which matches up with A into B plus C plus D. So C is your correct answer. Moving to the next question. What is the next question? The output Y of the circuit shown in the figure. Okay, almost similarly, same model. Okay, so as we already discussed, we are going to write the SOP expression in complemented form with respect to your output terminal to ground. Okay, with respect to output terminal to ground. Okay, so first, so F is equal to, okay, I'm going to write the SOP expression in complemented form. First, so how many parallel paths do we have with respect to output terminal to ground? So only one parallel path. So only one parallel path. So this can be written as A, B, C. This is C dash. C dash, the whole dash. Okay. So this can, so using De Morgan theorem, using De Morgan theorem, this can be further written as F is equal to, so A becomes A dash, B, so into becomes plus, B becomes B dash, again into becomes, yeah, into becomes again plus. So C becomes C double dash. Okay, so this C dash becomes C. Okay, so this is your final expression. So which matches with A. Okay, so A dash plus B dash plus C. So this is your right answer. Moving to the next question. Okay, so the logic functionality realized by the circuit shown below is. Okay, so we have to uh, find what is the logic function this circuit is going to implement. Okay, fine. So now here all the transistors are an NMOS. Okay, here all transistors are NMOS. Okay, and we know that when input to the gate is 0, input to the gate is 0, NMOS behaves as an open circuit. And similarly, when an input to the gate is 1, okay, gate is 1, NMOS behaves as an so this is the basic function that you have to remember. Fine. So now, mm, we can we are going to redraw the above circuit like this. Okay. So above circuit can be redrawn as like this. So this is a terminal B. Okay. And this is the terminal A. And output Y. So this is transistor T1 and this is the transistor T2. Fine. So the above circuit I have redrawn like this for easy understanding. So these are the two terminals B and B dash. B and B dash is terminal A. So fine, this is output terminal Y. So now, as we know that when input to the gate is 0, and NMOS behaves as an open circuit. Okay, so now case 1. So I'll take this circuit here. This is case 1. Okay, case 1. Okay, so here, if B is equal to 0, what do we do there? when B is equal to 0, what happens is transistor T2 is short circuited. Okay, it is short circuited. Therefore, output Y is equal to 0. So, the output Y is equal to 0. So, we'll check it out. So, when B is equal to 0 here. So, when B is equal to 0, what's going to happen? As I already told you, when input to the gate is 0, NMOS behaves as an open circuit. Okay, it's open circuit in the sense this becomes open circuit like this. So, what will happen to your Y? Okay, so Y is going to be equal to 0. Okay, because you don't have any connection between your input A S and Y. So, therefore, Y is equal to 0. And similarly, the second case. In case 2. Okay, in case 2. Okay, in case 2 is B is equal to 1. Then B is equal to 1. What will happen to your transistor T1? T1 is short circuited. Okay, T1 is short circuited and the output is going to be Y is equal to A. Output Y is equal to A. Okay, so check this out. So now when B is equal to 1, so we are going to put this is equal to 1. So when this is equal to 1, so your transistor T1, so when this is equal to 1, what will happen to your NMOS? It is going to be short circuited. It will be like this. It becomes short circuited. Okay. So what will happen? So this A appears as the output terminal. So Y is equal to A. Okay. So now we'll check it out. So now with the two terminals A and B. Okay. So these are the two inputs A and B with output Y. Okay. So what are the possible combinations? 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So now if you see here, when B equal to 0, Y is equal to 0. When B equal to 0, Y is equal to 0. Okay. When B equal to 0, also since it's open circuit, you don't have any output. So Y is equal to 0. So when B equal to 0, Y is equal to 0. And similarly, when B is equal to 1, Y is equal to A. When B is equal to 1, so B is equal to 1. Right here, Y is equal to A. What is Y equal to A? That means here it is 0, so here also it is 0. Here it is 1, here also it is 1. Okay, so now this logic, this truth table resembles to what? Resembles to an AND gate. Okay, when all inputs are high, the output is high. Resembles to an AND gate. So your logic functionality is an AND gate. Okay, okay, that's fine. Then we'll move to the next one. So next question, the logic function f of x, y realized by the given circuit is the logic function. So similarly, almost the same question. So I have to find what is the logic function. This diagram is representing. Okay. So now we'll check it out. First, we'll consider this is nothing but an NMOS circuit. Okay. Okay. So we are going to consider the NMOS circuit, and the inputs are the inputs of f of x comma y is equal to. Okay. As I already told you, is nothing but n complemented function of the SOP expression. Okay, complemented function of the SOP expression. So here, so this is your output terminal and this is your ground. So we are going to write the expression for uh, the NMOS circuit with respect to the output terminal to the ground. So here, if you see what is your SOP expression is, here what is your so you have two parallel branches. You have one parallel branch and this is your second parallel branch. Okay. So now first I will write the first one. So what is the input for this? Input for this is x dash and input for this is y dash. And similarly, the input for this is x and input for this is y. So now we'll write the SOP expression. Okay. So for the first parallel branch, this is nothing but x dash y dash. Okay. At the second parallel branch, it is x. And this is the complement. Okay, got it. So this expression can be okay. So this expression can be written as x dash y dash plus xy is nothing but x dash y dash plus xy is nothing but x x nor y. Okay, so the whole dash. Okay, so this can be further written as uh, okay. So this can be further written as x x or y. Understood? So your final answer is nothing but x. Okay. So now we'll move to the next question. So now here we are going to discuss a PLA problem here. Okay, the PLA problem. So in this problem, the question is given as a programmable logic array is shown in the figure. The Boolean function f implemented here. Boolean function f implemented here. Fine. So now here we are going to find first going to find the product terms for the three product terms. First, so we'll take like this. So I'm going to take this as x1, take this as x2, and this as fine. So now first, so as we know that in PLA is nothing but you have an underarray or array. So here in PLA, both underarray and the array both are programmable. So you have in PLD, we have three main classifications from. Okay. So in PLD, programmable logic device. Okay. PLD, you have three main classifications from PLA and PAL. PAL. So PLD consists of underarray and array. PLD consists of underarray and underarray and array. Okay. So based on the underarray and array, how it can be programmed, it is classified into three: from, PLA, and PAL. Okay. So here in PROM only array is programmed. Only array is programmed. In PLA, both array and underarray both are programmable. Array and underarray both are programmable. In a PAL, only underarray is programmable. Only underarray is programmable. Okay, so you can easily remember like this with this word. See from, you see. Okay. O. O refers to R and middle word A refers to and. Okay, so by this and the PLA is both. Okay, so that you will have an clear idea which is program. Fine. So here, so now we have, so this function f is going to have three product terms x1, x2, and x3. Okay, now from this we are going to write what is the product term for x1. So x1 is nothing but, see here, p dash q r, p dash q r, and x2 is equal to p dash q dash p dash q r, p dash q r. Got it. So x3 is equal to p q dash r, p q dash and r. Okay. So now therefore a function f is equal to addition of all this p dash q dash r, p dash q dash r plus p dash q r plus p q dash r, which matches up with C. Okay, matches up with the C option. So now move to the next question. Okay. So now, in this circuit shown, A and B are the inputs. Okay. A and B are the inputs, and F is the output. So what is the functionality of this circuit? So what is the logic function is going to implement? Okay. So in order to find the answer for this, so input B, so if you see, then input B is connected to the input B is connected to, so I will put the transistor as this as A. Okay, I put this transistor as A for your understanding. I will put as T1 and T2. Okay, T1 and T2. So input B is connected to the transistor T1 and input A is connected to the transistor T2. So now input so input B. Input B is connected to the NMOS transistor. That is NMOS transistor. Here I mentioned that as T1. Okay, NMOS transistor contrast T1. So what will be the status of the transistor? Okay, so if B is high, so if B is high, okay. So see, repeat. So your input B is connected to the transistor NMOS transistor T1, and if your input B is high, okay, this is high, you can see your output F is connected to your is connected to A. F is connected to A. So already we know that. Okay. So already we have discussed this here in the previous column. Okay. See here. So the input. Okay. So here when you give high here, B is high, what happens? NMOS behaves as a short circuit. NMOS, so when B is equal to 1 here, what happens? This behaves as a short circuit. Okay. So what happens? So F is connected to the A. This is what I'm trying to tell you. Okay. So in short, that's nothing but that is nothing but when if B is equal to 1, F is equal to A. Fine. Okay. Similarly, okay. Similarly, input A is connected to the input input A is connected to the NMOS transistor. Okay. Similarly, input A is connected to the NMOS transistor T2. So now if A is equal to 1, what will happen? Okay. Okay. Similarly, if A is high, A is high, okay, what happens? This becomes short circuit. So F is connected to the B. Okay. F is connected to B. So there is similarly, there is if A is equal to 1, F is equal to B. Okay. Right. And now, if both the inputs are A and B are 0, okay, if both inputs A and B are 0, what will happen? So if both inputs are 0, so this is A also, if it is 0, and B also, it is 0, what will happen? It will be an open circuit. Okay, so this will be an open circuit, and this will also be an open circuit. So F is equal to 0. Okay, so F is equal to will be equal to 0. So now we'll check this with our truth table. So we have two inputs A and B with the output. So the possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. Fine. So now, if B is equal to 1, F is equal to A. When B is equal to 1, okay, sometimes B is equal to 1, F is equal to A. F is equal to A is 0 here and this 1 here. Similarly, if A is equal to 1, F is equal to B. Okay. When A is equal to 1, F is equal to B. F is equal to 0. So it is 0 here. And you can see 1 is 1. Fine. And when both are 0, when both are 0, so what is going to happen? So this is not equal to 0 here. Okay. And both are open circuit. Okay. This is, okay, open circuit. So what happens here is VDD appears at the output. So both are open circuit. So what happens? Your VDD appears at the output. So it's going to be 1. So this truth table resembles to an okay, XNOR. Your option is D. Understood? And we'll solve one more problem. So for the circuit shown in the figure, P and Q. Okay, for the circuit shown in the figure with inputs P and Q, okay, with and output Y. What is the logic implemented by the circuit? So the same type. Okay. So all the you know that so in the PMOS circuit conducts conduct at logic 0. And n must conduct logic 1. Okay, logic 1. So now you will see case 1. You will see two cases. So in case 1, if P is equal to 1, what will happen? When your input P is equal to 1, and this is equal to 1, so what will happen? We have two mass flows. We have P mass, here N mass. So when P is equal to 1, what happens here? When P is equal to 1, and then the P mass conduct? No, it doesn't conduct. Okay, so it does not conduct. So that means it is else put is an off condition. And N must conduct. Okay, and P is equal to 1, what happens? N must conduct, and this does not conduct. Okay, so this N must will be in on condition. So what is therefore here Y is equal to? So what happens? So this is not going to conduct, and this is going to conduct, right? So what happens here? So we can again. So Y is equal to Q dash. Y is equal to Q dash. Next, case 2. Case 2, P is equal to 0. P is equal to 0. So we see what is the condition of P mass and the N mass. So when P is equal to 0, the P mass will be on and N mass will be off. Okay. So during that time, so P mass will be on and N mass will be off. So what happens? The Q will appear at the output. So Y is equal to Q. So now we look at the truth table. So with two inputs, P, Q, and output Y. 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So now, when P equal to 1, Y is equal to Q dash. When P is equal to 1, when P is equal to 1, okay, Y is equal to Q dash. Y is equal to Q dash. 0 becomes 1, 1 becomes 0. And when P is equal to 0, okay, when P is equal to 0, Y is equal to Q. So just write that 0 and 1. So this resembles as an XOR. Therefore, a function Y is equal to P XOR Q. Nothing but is an XOR operation. Okay, understood? So we'll stop video at this. We'll continue in the next week.